2 years ago, we were guessing about the universe. We squinted at blurry dots and traced shadows, thinking we had an idea of what early galaxies looked like, or whether alien planets even existed beyond our imagination. Then James Webb opened its eyes, and suddenly, the asterisks started disappearing. We weren't just detecting planets anymore, we were reading their atmospheres. We weren't just glimpsing faint dots from 13 billion years ago. We were seeing fully formed galaxies that shouldn't even exist yet. And that was only the beginning. James Webb didn't arrive to quietly confirm what we already knew. It arrived to challenge everything, rewriting the story of the cosmos. Moment by moment, the first real shock came from a single image. To the casual eye, it looked like starry wallpaper, but once scientists started analyzing it, they realized it contained thousands of galaxies. Not stars, galaxies. Each filled with billions of stars, scattered across a patch of sky no bigger than a grain of sand held at arm's length. SMRCS 073, a massive cluster, about 4.6 billion light-years away, offered more than just beauty. The gravitational lensing distorted the light from more distant galaxies, magnifying them naturally, letting us peek behind the curtain of the universe. Some of those galaxies looked too bright, too structured, too evolved. According to our models, galaxies back then should have been chaotic, tiny, just forming their first stars. Yet here were smooth, clustered systems, already showing signs of maturity. And that was only day one. Before full calibration, JWST had already forced us back to the drawing board. James Webb didn't just stare at the far reaches of the universe. It turned its infrared eye closer, at planets we'd only guessed about. Previously, exoplanets were silhouettes, tiny dips in starlight, giving us hints of their existence. Now, we could read their atmospheres directly. WASP-39b revealed carbon dioxide. WASP-18b and WASP-80b showed water vapor. But then came the weird part. WASP-17b had tiny silicate crystals floating in its skies. Like glass hail suspended in clouds, exoplanets didn't follow Earth's playbook. Their weather, chemistry, and atmospheres were alien in every sense. And for the first time, we could see it clearly. Closer to home, Webb continued to astonish. It captured Neptune with unmatched detail, mapping cloud tops, poles, and rings. Cheroklo, a tiny asteroid, revealed its own miniature ring system. Europa, Jupiter's icy moon, vented water vapor in real time, confirming active subsurface oceans. Even Comet 238P, Red, surprised us, missing carbon dioxide entirely, hinting it formed in warmer regions. Out past Pluto, Webb detected methanol and organic compounds on trans-Neptunian objects. These weren't inert relics, they had chemistry, history, and stories of their own. JWST proved it could teach us as much about nearby objects as it could about the distant universe. By 2023, deep field surveys began revealing galaxies in the first few 100 million years after the Big Bang. Fully formed, bright, and structured, CES 93316 existed just 235 million years after the Big Bang, far earlier than expected. JDGS Z130 followed the same pattern. Astronomers coined it the too early, too big problem. Galaxies shouldn't be this mature so soon, yet there they were thriving, forming stars at astonishing rates, challenging every timeline we thought we understood. If galaxies were this advanced, what about their central black holes? Active galactic nuclei in young galaxies appeared almost immediately. Says Cientonueva, only 570 million years post-Big Bang, showed a black hole already feeding. Direct collapse. Black holes, massive clouds collapsing into black holes without forming stars, offered one possible explanation. Quasars, luminous beacons powered by black holes, appeared more frequently than models predicted. Some amplified by gravitational lensing, offering unprecedented detail. JWST wasn't just observing the early universe, it was proving some of its most mysterious objects existed far sooner than we imagined. Then came the silent ones. Galaxies already done, forming stars within the first billion years, quiescent, mature, like elderly people in a kindergarten classroom. Nicknamed Sleeping Beauty galaxies, they posed a fundamental question: why stop so early? Was there a mechanism halting star formation, or were these galaxies a unique exception? Either way, they shattered assumptions that early galaxies went through a slow, chaotic adolescence. By 2025, Webb's gaze reached K218b, 120 light-years away, detecting dimethyl sulfide DMs alongside methane, carbon dioxide, and dimethyl disulfide, hinted at possible biological processes. On Earth, DMs is exclusively produced by life, specifically marine plankton. Scientists caution it's not a confirmation of aliens. Unknown abiotic processes could be responsible, but the odds are intriguing. Webb was no longer giving us shadows. It was giving us signals, testable clues about potential life beyond our solar system. Marking a first in exoplanetary science, in May 2025, MUMS Z14, the most distant galaxy ever observed, appeared light from just 280 million years after the Big Bang. Later, the Infinity Galaxy collision revealed two merging galaxies forming a near-perfect figure eight, complete with a supermassive black hole feeding at its center. JWST captured not just visual spectacle, but also processes shaping galaxy and black hole growth. Chaotic collisions, extreme environments, and rapid black hole formation were all visible in one image. JWST didn't just see far, it captured the first direct image of exoplanet SHIP 65426b, revealing clouds' molecular composition, temperature, and weather patterns. Closer to home, it tracked near-Earth asteroid 2024 Year 4, measuring surface composition, orbit, and impact probability. From distant galaxies to local asteroids, JWST proved itself a versatile, precise toolbox for every scale of astronomy. Galaxies formed faster than expected. Black holes appeared earlier than models allowed. Stars burned, galaxies matured, and planets displayed atmospheres stranger than anything we imagined. Webb didn't just confirm our guesses, it challenged them. It transformed astronomy from speculation into measurable, sometimes uncomfortable, clarity. And this is only the beginning. Thousands of observations remain in the pipeline, waiting to reveal secrets we haven't yet imagined. JWST isn't just seeing the universe, it's forcing us to rethink it entirely. And the next decade promises discoveries that will change everything we thought we knew about the cosmos. Webb also looked closer to home. Neptune's poles, cloud tops, and rings were captured with unprecedented sharpness. Chariklo, a tiny asteroid, flaunted a miniature ring system. Europa, Jupiter's icy moon, vented water vapor in real time, confirming subsurface oceans. Even Comet 238P, Red revealed unexpected chemistry, no CO2, only water, hinting it formed in warmer conditions than anticipated. Out past Pluto, trans-Neptunian objects displayed methanol and organic compounds. The outer solar system was alive with chemistry, history, and stories waiting to be decoded. Webb proved it could teach us as much nearby as it could in the distant cosmos. In 2023, deep field surveys revealed galaxies forming fully just a few hundred million years after the Big Bang. CES 93316 appeared only 235 million years after the Big Bang, fully structured, luminous, thriving. JDG SZ130 followed the same pattern. Too early, too big became the term astronomers used to describe the problem. These galaxies shouldn't exist yet, not fully formed. Their rapid star formation and mature structure defied models. If galaxies were this advanced, the next question was obvious. What about the black holes lurking in their centers? Active galactic nuclei appeared surprisingly early, says Nuebe, from just 570 million years post-Big Bang, revealed a black hole actively feeding. These findings revived the controversial theory of direct collapse, black holes, massive clouds, collapsing into black holes without forming stars, quasars. Those intensely bright beacons, powered by black holes, emerged far sooner than models predicted. Gravitational lensing amplified some of their light, offering more detail than astronomers had ever dreamed of seeing. JWST wasn't just observing it, was rewriting the timeline of cosmic structures, and then there were the galaxies that simply stopped forming stars, quiescent within the first billion years. No gas left, no activity. Sleeping Beauty galaxies. It's like finding an elderly person in a kindergarten classroom fully mature before anyone expected. Why did star formations stop so early? Could these galaxies ever wake up? Webb forced astronomers to accept that galaxy growth didn't follow a single rulebook. Chaos, speed, and unpredictability were the norm, not the exception. By early 2025, Webb focused on K218b, 120 light-years away. Its atmosphere hinted at dimethyl sulfide DMs of methane, carbon dioxide, and dimethyl diphide. On Earth, DMS is produced only by life for marine plankton. Scientists caution it's not proof of aliens. Unknown chemical processes might exist. But this was the first time a telescope offered a direct, testable clue about potential biology beyond our solar system. Webb was finally giving us signals, not shadows, data, not speculation. A subtle but revolutionary shift. It's easy to forget just how fast things changed. 2 years ago, when we talked about distant galaxies, most of what we said came with a giant asterisk. We thought we saw the first stars forming. We believed we had an idea of what early galaxies looked like, and when it came to alien planets, we were basically guessing, tracing shadows, and hoping for the best. Then James Webb opened its eyes, and suddenly the asterisks started disappearing. We weren't just detecting planets anymore. We were finding actual signs of what might be in their atmospheres. We weren't squinting at blurry dots from 13 billion years ago. We were looking at fully formed galaxies that, according to everything we thought we knew, shouldn't have even existed yet. And that was just in the first few months. Since then, James Webb has rewritten our understanding of the universe, one target at a time. From ghost galaxies that stopped forming stars billions of years before they were supposed to chemicals in exoplanet skies that don't belong there. If you were hoping for a telescope that would quietly confirm what we already believed, this isn't it. So let's look back, not at the launch, not at the hype, but at the work, the timeline, the things it actually found, moment by moment. Because the real story of Webb isn't in its design, it's in the discoveries. And some of them still don't make sense. We all saw the image, and it looked like a starry wallpaper. Nothing more than a tiny dot in the sky, magnified 100 times over. But once the shock wore off and people stopped saying pretty, the scientists started digging into the details, and that's when things got interesting. That single image, just one, showed thousands of galaxies. Not stars, not planets, galaxies. Each one filled with billions of stars of its own, scattered across an area of sky the size of a grain of sand. Held at arm's length, it was called SMA CSO 723, a massive galaxy cluster located about 4.6 billion light-years away in the constellation Vol. But honestly, the name didn't matter. What mattered was what it proved. For the first time, we had a clear infrared look into the deep universe. And it didn't just show distant galaxies, it showed warped light, lensed arcs, ghostly shapes stretched across space and time. That warping wasn't an error, it was gravity. Massive clusters in the foreground were bending the light of even more distant galaxies behind them. And those distortions weren't just beautiful, they were useful. Gravitational. Lensing acts like a natural telescope. It magnifies, it reveals. It lets us peek behind the curtain. So in that first image, we were already looking at galaxies that existed over 13 billion years ago, just a few 100 million years after the Big Bang. That alone was impressive. But here's the part that caught everyone off guard. Some of those galaxies looked too bright, too structured, too evolved, and that didn't line up. According to most models, galaxies back then were supposed to be small, chaotic, and still forming their first stars. But what Webb showed, even in that first photo, was something that looked much further along. Smooth structures, defined clusters, evidence of star formation that should have taken hundreds of millions of years, more than the universe had given them at that point. So naturally, the questions started piling up. Were these galaxies forming faster than we thought possible? Were our models of the early universe just wrong? Or were we looking at something else entirely? A different kind of structure built under different rules? And this was just day one, before Webb had even locked in its full calibration, before its instruments had been tested across the board. It had already sent us back to the drawing board. Not because the data was unclear, but because it was too clear. It didn't confirm our expectations, it challenged them. What's wild is that this wasn't some deep survey that took months to complete. It was a snapshot, a glimpse, proof that even in the blankest parts of the sky, there are entire universes hidden in the dark, waiting, quiet, until the right lens came along. That lens was James Webb, and in just a few hours, it rewrote our map of the early cosmos. A telescope like Webb wasn't built just to stare into the ancient past. It was also designed to look closer, not at galaxies billions of light years away, but at stars just down the street, orbiting their own little worlds. Worlds we've been chasing for years, guessing their shapes, estimating their temperatures, watching their shadows. And up until now, that's all we really had, shadows. When a planet passed in front of its star, we'd see a tiny dip in light. That's how we found them. That's how we measured them. It worked, but it was limited. You can learn a lot from a silhouette, but it doesn't tell you what the planet is. It doesn't tell you what it's made of, or what's in its sky, or if anything's living there. Webb changed that. Its infrared sensitivity made it possible for the first time to read the actual chemical fingerprints of an exoplanet's atmosphere, not indirectly, not through noise and modeling, but directly by splitting the light that passed through it and analyzing the spectrum one wavelength at a time. That's how we got the first clear detection of carbon dioxide on a planet outside our solar system. WASP-39b, a hot gas giant, 700 light-years away. That one single result proved the concept. It wasn't just hype anymore. Webb could read alien atmospheres. And then it went further. Webb found water vapor on WASP-18b, WASP-de-Lappenpoula-b, and GJ486b. These aren't friendly planets. One's boiling, one's practically hugging its star. But the point isn't that they could host life. The point is that we could read them, measure the thickness of their clouds, track changes in pressure, see signs of things like methane and sulfur dioxide, gases that mean something when they show up in the right combinations. Then came WASP-17b, and that's where it got weird. Webb didn't just find vapor or gas, it found solid particles in the planet's sky. Tiny silicate crystals, essentially glass, suspended in the atmosphere. The same way Earth's clouds can carry water. Droplets, this planet was flinging microscopic quartz around like hail. It was the first time we'd seen anything like that. And it made us realize something. Exoplanets don't follow Earth's playbook. Their weather systems, their skies, their entire logic might be different. Wildly different. And Webb was the first tool that could actually show us. But it didn't stop with exoplanets. Webb turned its gaze inward toward our own solar system. And even though these were closer targets, it still managed to surprise us. It captured the sharpest view of Neptune. In over 30 years, not just the rings, but the thermal profile, the pole, the cloud tops. The level of detail was unreal. Then it locked onto Cherokla, a strange asteroid with its own tiny ring system, and detected water ice. That's an object only a few hundred km wide, yet Webb could map its surface. Then it turned to Europa, one of Jupiter's moons, and detected plumes of water vapor venting into space. That confirmed what we suspected from older missions, like Galileo and Hubble. But this time, it was crystal clear. Europa wasn't just frozen. It was active, breathing, jetting out the contents of its subsurface ocean like a leaky faucet. And Webb was watching it happen in real time. Even Comet 238P, red, a small rock in the asteroid belt, got its spotlight. Webb detected water, but no carbon dioxide, which was weird. Most comets have both. This one didn't. That tells us that maybe this comet formed in a warmer region than we thought, or that its CO2 has long since escaped. Either way, That's a clue about comet formation, about solar system chemistry, about how water made its way here in the first place. And then, there were the trans-Neptunian objects, icy bodies way out past Pluto. Webb started picking up traces of methanol and organic compounds on them, too, helping us piece together what the outer solar system was like in its earliest days. These weren't just static leftovers. They had chemistry change, history. So, yes, James Webb was built to look far, but it turned out to be just as powerful when it looked near. Because every time it focused on something we thought we understood, whether it was a planet we'd already discovered or a moon we'd been circling, for decades, it showed us something we missed. In 2023, JWST started pouring in data from deep field surveys. One of the first things astronomers noticed was the sheer number of galaxies it was picking up in the first few 100 million years after the Big Bang. Not just faint blobs of light, not background noise, fully formed galaxies, dozens, then hundreds in places we thought were still empty space. And some of them were just wrong. Take CES 93316.